So this is a work from my master's studies actually, which I completed like over 3 years ago. And this paper was recently accepted to be published in Autonomous Robots. And it was an extension of a work we did for this IROS conference, a robotics conference, where we extended the results with further completeness and correctness results and algorithms and more experimental evaluation. But I will just here talk about the main ideas we have. So our motivation was that many robotic application domains use multiple teams of robots with heterogeneous capabilities such as search and rescue operations, exploration missions, service robotics, and cognitive factories. And the goal is for all teams to complete their tasks as soon as possible by helping each other, by lending robots if necessary. And our focus was on cognitive factories. And here we have multiple robots in different workspaces where some robots have tasks of carrying boxes while the others have more sophisticated tasks of building things or even, I don't know, doing some experiments or something. So everyone has their own workspaces, and these robots are endowed with high-level reasoning capabilities, and these factories should rapidly respond to changing customer needs. And these robots utilize sophisticated planning and decision-making algorithms. And the two challenges that exist in the cognitive factories is, one is hybrid reasoning for each team, so combining the discrete task planning with continuous feasibility checks and perception. And the other is finding an optimal feasible global plan for all the teams. And this can be done by finding an optimal coordination of robot transfers between teams. So like one team may have more difficult tasks, and it may be delivering a robot to that team would help it conclude its task much faster. So in our approach, we use knowledge representation and automated reasoning formalisms and the tools, and we introduce a method for hybrid reasoning by embedding feasibility checks into high-level representation and reasoning. We introduce a semi-distributed method to compute an optimal global plan for multiple teams of heterogeneous robots, where we find the coordination of the teams, and then we do decoupled planning. We evaluate the efficiency and the scalability of our method on realistic scenarios using state-of-the-art automated reasoners, and we have a video of robots, which I will show later on. So I will first start with how we represent and reason about the dynamic domain. We make use of ASP, and there was another work that's presented before about ASP, so I don't have to go into so much detail of how great it is. So it's a declarative programming paradigm that's oriented towards solving difficult problems. And the programs consist of rules of this form, where you have the head, which can be an atom, and the body of atoms. And so if you don't have a body, then this rule is a fact. And if the head is bottom, then this is a constraint. And the theoretical basis behind this is the answer says semantics. And why we like making use of ASP is it's quite expressive representation language, because it allows for aggregates, weight constraints, cardinality constraints, optimization statements, default negation, and access to external computation. And yeah, these are the publications in case you're interested to see about it. And so we can also describe actions with ASP. For example, if there's for describing the go-to action, you can describe the effects of the action in this form, where the robot going to a location at time t results in the robot being at that location at t+1. And you can also describe preconditions in this form, which says that the robot cannot go to a location where it is, if it is already there. And you can also describe the capabilities of heterogeneous robots. For example, you can paint, the robot can paint a box, then in the next time step the box will be painted. But if you have a dry robot, so a robot that cannot do painting activities, then you can forbid that robot to do painting actions. And furthermore, you can describe complex constraints with ASP. For example, here we have cardinality constraints, which says that the box should be carried with at least 2 robots. So this constraint is ensuring that this holds. And you can do optimal planning. So you can minimize the make span, the plan length, by minimizing the time that you reach the goal. And you can also give cost to actions, and you can minimize these total costs, where you give costs of the robot doing an action at a time t, and then you minimize the cost for each of the robots. And this will give you optimal planning. And you can make use of external atoms. What external atoms is highlighted here. It's making use of external computations and embedding them into the ASP programs. So here with the given input, you compute the truth value of this input, and then you output the result. And here the idea is to check whether from location 1 to location 2 there is a path existing. And you can do this computation externally by using a programming language like C++, Python, whatever, and then you return the truth value. And this says that a robot should not go to from location 1 to location 2 if there doesn't exist a path. And this brings us to hybrid reasoning. So the idea of hybrid reasoning is combining these discrete task plans with continuous motion plan. So if you have this task plan of going to a location, picking up a box, going to another location and putting down the box, you need to check for existence of a continuous trajectory between these 2 points, because there may be an obstacle and this may not occur. And such collision checks can be done by means of a motion planner, which we make use of. And what the idea is to have a precondition by making use of this external atom and describing this external computation in a programming language, and then embedding this feasibility check into this precondition. So here it says that the robot should not go to location 2 if there exists a collision, and this check is done with this external computation, where what we did was we created an environment where certain obstacles, then you determine the object locations using Kinect, and then you check for collisions using the Open Dynamics agent. And this allows for embedding external computations for continuous feasibility checks into high-level reasoning. And we made use of this approach to handle robot obstacle collisions. And another way was doing guided replanning with constraints. And here the idea is you compute a plan, and then you check for collisions of the robots using, again, the computations provided by ODE. And if the plan is infeasible, you identify the cause, you modify the planning problem by adding new constraints, and then you ask for a new plan. For example, here, if there are 2 robots that cannot pass diagonally from A to B, then you give it as a constraint and ask for a new plan in which such an action doesn't occur. And this approach was used for handling robot-robot collisions. And so far I described how we modeled the domain of these teams, and we made use of ASP in such forms. And then comes the question of how to find the coordination of these teams. And the idea is simply summarized here. So the idea is first querying the teams, and then collect the answers and finding a coordination of the teams, and then decoupling the plans. So what we have is, we have multiple teams of robots, heterogeneous robots. Each team has a feasible task to complete, and the teams can transfer robots between each other. So we have certain assumptions. So there's this privacy, where the teams do not know about each other's information. They don't want to share anything. And what we want is we don't want landing and borrowing robots between workspaces back and forth. So the robots can be transferred between 2 teams in a single batch. And there's also this third constraint where we say that the teams can borrow land robots only of the same sort. And our goal is to find an optimal feasible global plan with minimum X-span for all teams with at most K steps, where certain number of robots of certain type can be transferred. So all these are inputs to the problem. And the idea is to make use of a mediator, where this mediator also doesn't know anything about the teams. And what it does, it gathers information from the teams with yes/no answers about whether and when the teams can help each other. So here, I won't go into so much detail about the questions, but the queries are in this form, where you ask whether they can complete their task in a certain step, whether they can complete their task in a certain step if they land some robots of some type, or if they borrow some robots of some type. And a mathematical model of this coordination problem is done based on these team's answers, and then comes the finding a coordination, where you compute the coordination using constraint satisfaction, which were provided from the answers of the teams. In more detail, we have two phases. In one, the mediator gathers this information from the teams and then finds a coordination which guarantees optimality, and then it does decoupled planning, where the necessary information about the coordination is passed to each team, and each team computes this optimal feasible local plan. Then the local plans are decoupled into a global plan. So this is just an example, which I don't have time to go into detail, but just to show that you can collect these yes-no answers, and then the idea is just to find a function, a collaboration function, which tells that which team should land which type of robots at which step to which team. And that's the problem that we have. And we modeled this problem, computational problem, and with the provided inputs of the answers that we collected from the teams, and we infer some further information from the answers, like the earliest time where a team can land a certain robot, or the latest time where a team can borrow a certain robot, and such. And then the output should be a collaboration between these teams. And we prove it to be, the problem to be NP complete. And we model this problem in ASP as well. When once the collaboration is found, the mediator informs each team about the collaboration. It just says that, okay, you should land these two robots at this time step, and then it says you should borrow these robots at this time step. And then each team computes their own feasible local plan subject to these given constraints. And then the union of these local plans give us a global plan. And a video. So here, if it's okay. So here, we have two teams, and they have different tasks with different number of robots. And we described this domain in ASP, and we queried the questions, and then we found the collaboration. And this is a video that shows that the collaboration is indeed feasible, and they're able to execute them. There's also an obstacle, so there's no collision with the obstacle. And at some point, they land these robots to the other team, where we also consider some delay time. Then the team one borrows the robots and continues executing the plans. And So about the experiment evaluation, I again won't go into so much detail, but the idea is this parallelization, and it ensures us that the approach is scalable, because with the parallelization, the mediator asks each team these questions, but the questions don't rely on each other. And each team can compute their answers to the questions in their own cores, and each of the questions that are asked to each team are also not related to each other, so everything can be parallelized. And this makes it scalable. So even large problems with 144 robots of 4 types, up to 42 robot exchanges with max span up to 29, this can be solved in a few minutes. We systematically investigated the role of each parameter on the computational efficiency and plan quality. I will mention just a few. So if we allow more robots to be exchanged between the teams, this results in shorter optimal plans as expected, because the teams becomes more helpful to each other. And this hybrid reasoning, of course, increases computation time, but it also gives us feasible plans, which also may end up being much larger, giving much larger plan lengths. So without hybrid reasoning, you get maybe shorter plan length, but it's not a feasible plan. But with hybrid reasoning, you're able to get a feasible plan in a bit longer time length. And the coordination finding is, if you involve more heterogeneous robots, it does make it a bit more difficult to solve the problem, because there are more constraints to be considered. And to conclude, there were some works on decoupled planning, where people impose certain constraints for the teams for their local plans, or they exchanged certain information, or certain negotiation was done. And ours was a different approach because we had this mediator and that doesn't know anything about the teams, and just questions were being answered. And yeah, to conclude, we represented this cognitive factory domain with multiple teams of heterogeneous robots in ASP, and we did hybrid reasoning for each team, where we combined this discrete task planning with feasibility checks. We also made use of optimization of plans by minimizing max spans and making use of total cost of actions. And we introduced the semi-distributed method to compute an optimal global plan. We again formulated the problem in ASP, and we have experimental evaluation and some demonstrations. We have more videos. If you like, you can just look up the website. And yeah, that's how it is. Thank you.
So, time for some questions.
Thanks for the talk. I have a quick question. So when you say optimal coordination between robots, does it correspond to any geometric instances, or do you mean something else by the optimality in coordination between robots?
Geometric instances?
I mean, what do you mean by optimality here?
I mean, optimality in the terms of the plan length, the optimal global plan that
So-
each team computes.
So optimal coordination means?
Did I say optimal coordination?
Yeah, maybe I misunderstood then.
Yeah, it's not, yeah, it's
Okay.
just the coordination, so it's not really optimal, it doesn't have, I mean, it just needs to be within the time limit that we give, but it's, probably should not say
Okay.
optimal coordination. Sorry.
Okay, thank you.
What is the motivation or the reason behind using ASP? It's because it answers set programming for modeling. Is it because you're using general purpose solver, ASP solver, or have you implemented your own model here? So the question is, why are you using ASP instead of other modeling
yeah,
formalism?
I was expecting such a question, actually.
Okay.
I mean, yeah, because ASP is quite expressive language, and it's easy to describe these constraints that you want to express, and with these complex constraints and everything. And it's not only doing planning, but it's also able to solve much more difficult problems. And yeah, we just stick to ASP. And it's for agents, actually, I think Tim also mentioned this in a previous talk, where it's much easier. You describe the domain in one encoding about all the multiple teams, and you find all the plan for all these teams with concurrent actions and everything. So it makes it much compact and easier.
Are you using any general purpose ASP solver, or have you implemented your own solution?
No, there are automated reasons out there like Klingo.
So you're using, okay.
Yeah, we made use of Klingo in this one.
And have you thought of implementing a fully distributed approach with no mediator in your system, or
No. Like, what do you mean by?
not using the mediators or agents, the teams
The agents,
communicate each
so-
other? Yeah, without
Yeah, so
using-
we didn't want the agent to communicate to each other, so we thought of this mediator. So yeah, no, we didn't consider that.
Okay, so let's thank the speaker again.
Thank you.